start without a preface. Custom allocators is a very well-known area in system programming for many years. This is just a reminder, this is not my picture, just to show you what we are talking about. The advantage against the standard methodologies of memory allocation, malloc, allocator, are very well known. If you can apply them, then allocation of memory is just putting the pointer back or forth, no request to the core of the OS, and no commentary tables showing where, what address goes where in the memory. That's why they are very high productive comparing against malloc, and if you have an opportunity to apply them somewhere, they usually applied. Custom allocators, there's a lot of literature on that and research articles, various algorithms. My presentation is devoted to how to apply custom allocation of memory for real big projects. So we see a large project, it can be a compiler or something or a game. And the question is, can we, through partially substitute malloc and use custom allocators and increase the productivity of this large app? If yes, then how? In the project, there are thousands or hundreds of malloc sub-operations of memory allocation. Where we put a custom allocator, what exactly we should use, how architecture will look like of this substitution, for it to be developable and understandable and modifiable. There are a lot of works devoted to custom allocators in real large projects, how to effectively apply it in practice. Well, I do not see many of them now. Definition of such methodology, application in practice of custom allocators in large projects. My work is devoted to this subject. So the results I'm going to discuss today in the methodology is executed in a large project, a whole compiler of shaders for a graphic processor. That's why illustration of utilization of theoretical results for this project will also accompany the presentation. So before we use custom allocator in a large project, we need to answer two main questions. What the questions my presentation is answering: what to change and how to change. What to change? To answer this question, we need analysis of the source code and the algorithms. What program modules and what allocation of memory for what structures of data we can use various types of allocators. Where and how, and what type of it. How to apply this is the next question. So we need instruments, we need effective object-oriented library of such allocators to change, to make it a painful process when changing the source code, and so for this code to be enhanceable and understandable. What to change and how to change in a large project. Let's move forward. I will start answering the second question. This is how to change. The architecture offered for custom allocator is object-oriented, and it is applied in the project. This is the library of custom allocators. It is based on 3 levels and use a sample methodology. C++ allows us to manipulate the samples. This is the main box template. It allows us to make templatable 2 realities. So the type of data for which we have custom allocator and what allocator exactly. Client type from strategy. Client type is, for instance, the name of class. Memory, for instance, where we will allocate memory through custom allocator, and the strategy. Linear stack, linked list, or something else. So this template has 2 features, strategy and client type. The main methodology is allocate, release, and property strategy, the type of allocator. Next level, it goes here. Custom allocator is a structure from which the program is taking the memory. So through malloc, we highlight one page. Malloc is a function of the system call to the core of the operating system that gives you the address of memory. Yes, we just do not have enough time. In my article that will be published soon, I have all the terms, all the definitions. I just do not have enough time to explain all that. We highlight the page through malloc, and then the program, when calling to the memory, just cuts out of these 4 kilobytes, it cuts pieces of memory. Next, classes that are doing an algorithm, linear or stack. They have 2 main methodologies, cap memory and release memory. To get memory and to release memory at a certain address. And then we have instance of this class. It executes all algorithms at low level to get to release linearly. So these are the cases of implementation program code for all the levels. How the level looks like. Strategy, stack pool, how it looks like on the level of template and on the level of declaration at the highest level. When user wants to apply something from this library, that's how he declares the allocator. He says what he's allocating, the vectors, and according to what linear strategy. What he's going to allocate, bit vector, and what strategy, stack. Compiler we are talking about is based on LLVM technology. Let's move on. I will skip this. This is an example of execution of one of the methodologies on the lowest level, how to release memory. And now let's go to answering the first question. We had a look at the architecture already. This slide shows proposed workflow and the methodology through what stages we need to put through our large project to effectively execute custom allocators in it if there is an opportunity and to increase its productivity. Commenting all the stages. First stage, which is called wrap in flocks, is as follows. You need to profile all the memory operations, all operations where we go for memory or release it. And for this, you need to wrap all mallocs, allocs, and reallocs in new and delete. You should wrap all them. Some functions that will give us information when executing a program. How much memory is asked for, by whom, and for us to be able to compare release and grab memory operations. Some details on how these wrappers work, how we wrap, and I will skip that because we do not have enough time. These are the malloc, for instance. It is changed for a wrapper. The log is showing what line of code, how much we asked for, and so on. And this is how free is wrapped: file, function, line, and PTR, the address the memory is released. And C++ operation, that's how it wraps. I'm not going to comment on all the lines. Next, manual recheck. So this was automated wrapping, but there are some challenges sometimes that make us manually check whether everything is correct, is wrapped correctly. Next stage is run it project, compiler, game through wrappers. We accumulate information on all operations with the memory. Next stage, searching hotlines. We search for lines where the grabbing the memory is going in the most intensive way. And such lines are the candidates for changing mallocs in them for custom allocator. I call them hotlines. We are trying to find them. Next, recognizing patterns stage. For each hotline, we need to understand what custom allocators should be effectively used in here, or none of them, or malloc should stay. Let's look at recognizing patterns in more details. How recognizing what it is based on, what strategy is the most effective. We need to structure a chart allocating memory in this hotline and releasing memory. So this chart is a typical example where linear strategy is the most applicable. Memory is growing, and then allocation of memory is going on, and the same sequence of releases, because the linear allocator is not doing the release.
Here is a picture, artificial, the graph, which also is okay for linear, but not as good. You can see it is not a monotonous increase, but some smaller fraying, but totally linear allocator also is applicable. And this is the picture, and the pattern shows that linear allocator will be bad because fraying is not done till the end, and then the memory is allocated up to the peak. It is going to be fully lost. It's going to be waste memory because the linear allocator cannot free it. Here's the typical custom allocator. Well, the characteristic is that allocating memory and the corresponding freeing happens at the same level, because what is the allocator? Because the last memory using the principle of stack is freed. Here is one allocated, at some point it is freed. When the whole memory is freed, and you can see at the same level, allocating the same level. So if we have this kind of picture, well, it is very well applicable by stack allocator. And here you can see when the memory is allocated by similar chunks. Ever-growing lines, they are of similar length. So as a result of using those compilers, we've allocated some in separate classes of hotlines in the corresponding classes, and with this or that strategy well applied. In the left table, they're all here. And then what you have to do is to understand who calls the memory to effectively implement the custom allocator. So for this, the next stage, which is called backtracing. Using database, you set the breakpoints for this malloc, and you collect the backtraces set to understand who generates memory, where to put the allocator. So the results of the backtracing are in the right table. It's the distribution of calls and backtraces by passes of compilators, and you can see passes LLVM, which those who use it all know what it means, and the percentage of those calls of hotline, who's going to be the owner of the allocator, which pass. The next stage, according to the methodology, is the tuning. Tuning is a service stage. For instance, if we have the stack allocator, the regime of calling destructors can violate the stack sequence, then you have to replace this destructors to really free them in the same way they were allocated. Then the most important stage follows. It's a design of architecture. How much time do I left? That's it? 20 minutes have passed. Okay, architecturing, 3 patterns were identified. Typical, and the way each pattern uses the custom allocator, and you can read it in the. Well, we changed the code. Then here are the results. First of all, they show how the allocators behave, the typical behavior of standard, and how the useful memory volume changes. So we allocate and then free. So for stack allocator, the results for bigger shader, and this is for the smaller shader. So here the graph shows. Look, here is here's the total picture, and this is the detailed pictures in different parts of it. The differences of behavior are the differences of passes of compilers. Here is one pass. Here is the memory works this way. On another one, So I built up pictures with borderline between passes. The allocator is the same, the pool is the same, but when one pass finishes, another one starts. So here is the borderline of passes where the allocator behaves different. The results for a bigger shader and the chunk size of 8 kilobytes. So the big shader. Time spent to allocate memory for a bit vector was decreased by 2 times without a custom allocator. 1 millisecond with custom allocators, it's 500 milliseconds. And I would like to draw your attention to the fact that it's valid only for one hotline. It's not high productivity of the whole program. It's just only for one line. The total time spent for one malloc line decreases 2 times. Then let's move on about the results to finish it. So those are the configurations we use to do the experiments. And that's the table that shows reduced time of shader compilers. That's the final table. So it was a real project, a real game with a lot of shaders in it. And the multiple shaders was put through the compiler with all necessary workflow according to the methodology was done. All custom allocators were introduced. So upgrading or increasing productivity is 10% for this project. Possibly for some other project, productivity might be even higher. Well, 10% is also a good result, which shows the viability of this methodology. In conclusion, I would like to say that besides methodology, there are some tasks of automation and transformation of programs for different stages. For wrapper, it's to wrap memory operations. For hotline searching, it's some statistical packages which will allow you to identify backtracing. It's cluster analysis of reverse classes to identify the distribution by classes and passes. And the most intellectual task is for developing how to transform the code to implement architecture. That's the most complicated transformation. Currently, it is done manually, but it requires embedded language. And the total script is a conclusion which combines it all. Thank you very much. Sorry, well, it's sort of not, we sound a little bit clumsy, but you can read in the article, in my article. Microphone. The main idea is methodology of introducing custom allocators in a big project, and as a result, high productivity. Thank you very much. Thank you very much for the representation. Me, as a developer of operational system, is question. With modern allocators, malloc, mostly they're implemented as zone allocators, and this call, and they're not always used, and that's quite a rare thing because usually it reserves a certain number of zones, and allocating memory, it might not address the nucleus, so the core, but to rewrite it to custom, well, very often it is quite tangible and not always performing well. Haven't you thought about fine-tuning your allocator, maybe increasing a specific number of zones for applications? Or yes, I was thinking about that. In my work, there's the list of tasks for future development, and I would like also to say that there's also mentioned that after the changes of program code, there's analysis, measurement, and testing done. And as I said, when mallocs are replaced, we can have either improvement or degradation. And then the conclusion is drawn that the custom allocator is not needed here. Certainly. Thank you very much. My question about pattern recognition. I would like to see that slide back with the graphs. And they look like freed memory against the number of allocation. Unfortunately, there is no graph with no pull strategy. So a scenario might be, well, we allocate thousands of smaller objects, and they will be freed in one. And in this case, the pull allocator would go well, and stack not so well. So the question is how to identify which is best here. Maybe we take into account the address the object was allocated and freed in. Certainly, analyzing a pattern recognition, you have to compare and benchmark the addresses permanently. So, where the memory is allocated and where it is freed, of course. So that's how it is based. Thank you. Thank you. And of course, it's all comparison. The last question. And did you do any surveys in automation replacement of allocators with custom allocators? Well, automation, at the end, I have enumerated automation objectives and tasks. All those tasks are partially automated, but of course require fine-tuning to combine them into are commercially usable. So, so far we need some manual testing. But so far, yes, it has been automated, almost all of it, because if a project is big, well, you will not be able to do it manually. But still, it is a raw thing. That's the number 2 task. The first one is engineering, then, and this is program transformation. Thank you very much. The very last question. Thank you very much. My question is, if you use sanitizers, because they work with standard memory allocators and allow you to find errors when you go to the borderline of other chunk, how do you solve this issue with custom allocators? Do you proceed? Do you move forward? Well, I can tell you, of course, maybe we do it offline because it's a very good question, and I can tell you exactly about such problems and how we solve them for custom allocators. If you're interested, let's do it offline during the break. Let's meet, and I will tell you because we don't have time here. Thank you. Thank you. Excellent answer. I'm not evading, but I'm ready to provide you details. Okay, thank you very much. The next speaker